Welcome back, folks. This is Chapter 3, Atomic Structure and the Periodic Table for Chem 1030, General Organic and Biological Chemistry for the University of Cincinnati. I am Professor Joseph Lamb, and today we are going to be focused on something a little bit different. If you remember from our last chapter, we really focused in on the mathematical aspects of chemistry. That is, what are the basic mathematical things that you need to be able to do in order to be successful in a chemistry class? Well, today what we're going to do is we are going to start looking at the structure of molecules, and in order to do that, we need to break it down even further and look at the fundamental structure of what makes up everything. That is, what are atoms, what components make up atoms, how are they put together, and how that information gives us an idea of their physical and chemical properties. That'll also lend us to understanding how the periodic table is organized, because it's organized based off of properties of individual atoms and elements, and really dig into the true functionality of the periodic table, why it is such a beautiful and elegant literal piece of art. So hopefully you'll enjoy today's lesson. You'll get a better idea of why the periodic table is designed the way it is, and really give you a fundamental understanding of what atoms are, how different atoms are different from one another, which makes up the different elements on the periodic table, and how that periodic table is organized. So what we're going to do to start off with is look at our learning objectives just like we always do. And I'm just going to run through these relatively quickly. We need to be able to specify electrical charge, relative mass, and location within an atom for each of the three major subatomic particles. Define the term atomic number and mass number given these two numbers, and determine the number of protons, neutrons, and electrons that are present in any given atom. We're going to define isotope and write the complete chemical symbol for given isotopes. Calculate average atomic mass for an element from isotopic masses and percent abundance. So yes, there will be a little bit of math associated with this unit, not nearly as much as the last one. We need to know the organizational basis of the periodic table, why it's organized in a specific way. Specify periodic table locations based off of the group and the period. Know the names of specific groups. Distinguish between metals and nonmetals and their physical properties. Understand the concept of the electron shell, subshell, and orbital, and classify elements based on its periodic table location with certain named groups. There's a lot more to this than what we're going to cover in the scope and sequence of this course, so if you're interested in more of that, I have plenty more videos that go through and dive in with all of those details, but without further ado, let's go ahead and get started and talk a little bit about what atoms are. So many of you are probably taking notes either with a pencil, maybe a mechanical pencil. You might be taking it with a stylus. If you're taking it with a stylus, just assume that it is a pencil. But the stuff in your pencil, the thing that you're holding in your hands, it's the thing you're writing with, it's not really called lead. A lot of times we utilize the term lead to describe the material that is inside of a pencil, but that is completely false and inaccurate. It is actually graphite. Graphite is made up of carbon atoms, whereas lead is made up of lead atoms. They're very, very different. If you're holding a lead pencil, it would be much, much heavier than that of a graphite pencil. And I have a lovely graphic down below of what a pencil looks like in case you were not aware. Did you know that the sharpened part that you can't write with is called the collar? I didn't think so. And well, if you did, more power to you. But but if you were to cut the but if you were to cut the graphite in your pencil and you were to repeat that over and over and over again, many times, and over and over and over and over, what you end up with is fundamental particles. So could you divide it forever, or would you run into some basic fundamental particles? In terms of time, you're probably going to be doing it for the rest of your life because atoms are very, very small. But eventually you are going to get to a point where you can no longer divide the pencil or the parts of the graphite in the pencil into smaller components. And the reality is this is a fundamental question that has been asked for thousands of years. It goes back to an ancient Greek philosopher called Democritus. And Democritus came up with the concept of the atom, that materials are made up of small fundamental units and that different materials are made up of different fundamental units. But at a large scale, matter appears to be continuous, right? We can't see these individual atoms. We can't see these individual components that make up matter. And it was thought to be so up until about 200 years ago. Many people think that chemistry is a very, very old and outdated science, and that is not the case. Chemistry is relatively new when we think about science and how long we've been working and experimenting with a variety of different things in the universe. But eventually you end up with atoms if you keep dividing it. It literally comes from the Greek term meaning indivisible. And so to understand matter, we need to understand the fundamental building blocks that make that up. I know that I've talked about this quite extensively in this course. But atoms truly are the Legos of the universe. They make up literally everything, and how you combine those atoms and how you put them together determines the structure and the function of the molecule that we're looking at. So in order to understand what differentiates the graphite in your pencil from how your tablet, iPad, or Microsoft Surface or whatever works, we need to understand individual atoms, what they're made up of, and that determines how they specifically function. And there's a long history on how the current model of the atom was developed. I mean, we go back to 1803, we're talking 220 years ago. But John Dalton was one of the very first individuals who came up with the idea and recognize that atoms of a particular element differ from other elements that are on the periodic table. The problem with that theory, though, is that atoms aren't indivisible. They're actually made up of subatomic particles. Now, in 1803, this is not something that can be researched or individuals can't go through and see. There was not a lot of research into that. But John Dalton came up with his atomic theory, and there are 5 main postulates to that atomic theory. You don't need to know those, but definitely go and take a look at those and get an idea of how those continue to provide us with truths about chemistry today. There's only a handful of them that were inaccurate, one of them being that atoms aren't indivisible because we do have particles that are smaller than that of an atom. J.J. Thomson discovered electrons, which are negatively charged particles that are found inside of an atom, and developed what's called the plum pudding model, which shows that the electrons, which are negatively charged, are scattered through a spherical cloud of positive charge. So recognize that atoms are neutral. They don't have a charge associated with them, but the positives and negatives kind of cancel each other out. Unfortunately, this was disproven by Ernest Rutherford, who ended up firing some alpha particles at some gold foil and ended up discovering that some of them actually bounced off. And in order for those those alpha particles to bounce off, there has to be something in the central part of an atom that causes those deflections. We'll actually discuss that in a little bit of detail here in just a moment, because this is one of the most fundamental and amazing discoveries of the current nuclear model. But he did recognize that there is a dense, positively charged center of an atom, which if you've taken any chemistry class before, you're familiar with as the nucleus. Niels Bohr later on came up with the planetary model of electrons, kind of giving the idea that electrons orbit the nucleus very similar to planets around the sun. That gave a little bit of an idea of how electrons exist outside of the nucleus, but it did not really give a fundamental explanation of how moving electrons don't really emit energy. They don't collapse in the nucleus, and the model doesn't really work for atoms that are quite heavy. But in 1926, Schrödinger came up with the idea that electrons don't orbit. They exist in 3-dimensional regions called orbitals, where it's an area that's around a nucleus where you're likely to find an electron. It's a little bit confusing, but I would be remiss if I did not give you an opportunity to see all of the different models that exist in regards to how the model of an atom has changed over the course of the last 200 years. While atoms are the smallest fundamental unit of elements, we can actually break that down even further into smaller particles. These are called subatomic particles, literally meaning smaller than an atom. And there are 3 primary types of subatomic particles that you're going to need to be aware of that make up all atoms. There is the electron, and an electron carries a negative charge, a proton, which carries a positive charge, and a neutron, which is considered neutral and carries no charge. And what I'd like you to take a look at down at the bottom is not only the charges, but take a look at the relative masses of each of these. An electron is significantly smaller in mass than that of a proton and a neutron. In fact, protons and neutrons are very, very similar in terms of mass to each other, but electrons are much fundamentally smaller. In fact, if we take a look at the relative mass here, if the mass of an electron is considered 1, protons and neutrons are nearly 2,000 times the size of an electron. So protons and neutrons are much larger. I'd like you to know the relative size of each of these as well as their charges, because that becomes very important when we go through and try to determine the number of protons, neutrons, and electrons given an atom. So, like I said, the most important experiment, or one of the most important experiments here rather, is the Rutherford gold foil experiment. The Rutherford gold foil experiment conducted in 1909 disproved the plum pudding model, which we discussed previously, which was that idea that there are volumes of positive and negative charge that are present in atoms. An atom is essentially empty space, just with positive and negative charges that are associated with it. So because of this, what Rutherford did is he designed a device, this alpha particle emitter, and basically what it does is it shoots little tiny atoms of helium in this little box. This box is made of lead because alpha particles are radiation. Radiation can be quite dangerous. But this little beam is shooting at some gold foil, and what he anticipated was that because atoms are essentially just empty space with positive and negative charges associated with them, that the alpha particles would go straight through. And so there's a detection screen that is around the gold foil, and what he anticipated was what you would see in the very first part of B there, that all of the alpha particles would go directly through the atom, none of them being deflected. However, what ended up happening was the one below that. Most of the particles did move through and go directly through the atom, but some of them were deflected. In fact, some of them were deflected so much that they came back towards the alpha particle emitter. Well, in order for something to deflect, it has to be hitting something. And so that gave Rutherford the idea that there has to be something small and dense, because first off, in order for deflections to occur, it has to be more dense than the alpha particles. So otherwise it would cause the nucleus or the particle to move. So whatever it's hitting has to be dense. In addition to that, it also has to be relatively small because very few of the alpha particles actually deflected. If lots of alpha particles deflected, that tells you that whatever's causing the deflection is larger. And so as a result, you would get more deflections. And what this ended up telling Ernest Rutherford is that there is a small, dense component of an atom, which we know today as the nucleus. And so let's break down the arrangement of those subatomic particles in a little more detail here. All protons and neutrons are found inside of the nucleus. The nucleus, again, is a small, dense, positively charged center of an atom. It makes up 99.9% of the mass of the atom because, if you remember, protons and neutrons are nearly 2,000 times the size of electrons. Electrons are found in a large region around the nucleus, moving quickly and randomly. We also utilize the term nucleon to describe any particle that's found within the nucleus, so that would be considered protons and neutrons. Now, this model here on the right-hand side gives more of an example of a planetary model. That is the model of Niels Bohr, which is not exactly the best example because, as we discussed before, electrons don't orbit the nucleus like planets around the sun. They kind of exist in these regions that are called orbitals. Again, the orbital concept really is beyond the scope and sequence of this course, but it is important to give you an idea that what you're actually seeing on the right-hand side here is not 100% historically accurate based on what we currently know of the model of an atom. Now, atoms are generally neutral, and what that means is that they have no overall charge in the atom. Well, if in order for something to be neutral, the number of positive charges has to be equivalent to that of the number of negative charges that are associated with it. So in most neutral atoms, the number of protons is equal to that of the number of electrons. That is, the number of positive charges in the nucleus are equivalent to that of the number of electrons that are around the outside of the nucleus. Just to give you an idea of relative size, if the nucleus of an atom were the size of a baseball, then the diameter of an atom, that is, the relative size of the atom, would be around 2.5 miles. So think about that in terms of how much empty space there is, and then also think about what atoms are in general. Atoms are mostly empty space, but atom makes up all matter. So by definition, all matter is mostly empty space. And that is amazing to consider when you think about when we actually look at things, when we're holding something that is mostly empty space, yet we see something solid. It's very, very weird to think about it, but when you get on a microscopic, sub-microscopic level, things in terms of chemistry and physics get really, really funky and really, really weird. So, again, just to put some things into perspective there for you. So I'd like you to take a few moments, go through and determine the answers to these questions. How many of the different subatomic particles carry a charge? How many electrons are needed to equal the mass of one proton? And atoms as a whole are neutral because of what reason? Take a minute, pause the video, and we'll come back and discuss these answers here in just a moment. Welcome back. Again, let's break some of these questions down. The first one says, how many of the different subatomic particles carry a charge? That is 2. Protons carry a positive charge and electrons have a negative one. How many electrons are needed to equal the mass of one proton? It's roughly 2,000. 1,800 electrons is perfectly fine. Again, it depends on the source that you're looking at, but as long as you're roughly within about 1,800 to 2,000, you should be in good shape here. And atoms as a whole are neutral because the number of electrons is equal to the number of protons. So just keep these fundamental ideas in mind as we continue to work through and understand the fundamental internal structure of atoms. So I would like us to break out our periodic table because our periodic table contains some very, very important information. I know we haven't used it a whole lot yet, but it is one of the most fundamental pieces and tools that chemists use on a day-to-day basis. It breaks down and provides us with so much useful information that we really need to take into consideration what it is offering us. The first thing I want to talk about is what is called the atomic number. The atomic number is the number of protons that are present in an atom. It is also the same as the very large number at the very top of each individual element on the periodic table. So for example, the atomic number of hydrogen is 1. That means that hydrogen contains 1 proton. The atomic number for helium is 2. That means that helium contains 2 protons. 3 for lithium, 4 for beryllium, etc. The mass number is the number of protons plus neutrons that are present in an atom. This is information that you do not find on the periodic table. That is an information that you'll find or develop a little bit later on. But again, I want you to just understand what the fundamental concept of the mass number is because we'll be utilizing it a little bit later. For neutral atoms, the atomic number is equal to that of the number of electrons. Remember, the atomic number is equal to the number of protons that are present in an atom. And because atoms are neutral, the number of electrons will be equal to that of the atomic number, hence the number of protons that are present. And again, just to reiterate, the atomic number is also equal to the whole number present on the periodic table of elements. So if I look at potassium, which is K, number 19 on the left-hand side here, that tells you that potassium has 19 protons that are found inside of the nucleus. So an atom has an atomic number of 5 and a mass number of 11. Let's determine the number of protons, neutrons, and electrons in the atom. So the very first thing we want to take a look at and understand is the atomic number. Remember that the atomic number is the number of protons. And in a neutral atom, the number of protons will equal the number of electrons. So in this case, we can easily figure out the number of protons and electrons because both of those would be 5. Remember that the mass number is the number of protons plus neutrons. So basically, this ends up becoming a math equation. The mass number of 11 is going to equal the number of protons, 5, plus the number of neutrons, which is unknown. And so we just do a little bit of math there. We take 11 minus 5, and we end up with 6 neutrons. So again, as long as we understand the fundamental concept of where we're finding the atomic number and what the mass number represents, we can very easily calculate the number of neutrons and electrons that are present. Now, there are a variety of ways I may ask these types of questions. We'll look at different notations, but the fundamental concepts are still the same here. So make sure you take this information and apply it to some of the stuff we're going to look at here in just a couple of moments. Now, often, the mass number and the atomic number of a given atom are often specified using a specific notation. So the very first thing you want to look at is in the top left-hand corner, you see the mass number. Remember, that is the number of protons plus neutrons. So the number for A is always going to be greater than the number for Z because Z is just the number of protons. A here is going to be protons plus neutrons, which is the mass number, and Z is just the atomic number, which is the number of protons. So A will always be bigger than Z. And then the symbol just represents the chemical symbol of the element that's present on the periodic table. So we should be able to determine the number of protons, neutrons, and electrons from this notation, as well as be able to work backwards and utilize the notation to determine the number of protons, neutrons, and electrons as well. So given that information and the information that I've posted up here, I'd like you to take a couple moments and go through and try to determine the number of protons, neutrons, and electrons that are present in these particular atoms. I'll give you a few moments, pause the video, and then we will work through these together here in just a moment. All right, so I've given you a little bit of time to take a look at these. Let's look at the very first one here. We have F. If we take a look at the bottom left-hand number, remember that tells you the number of protons. So the number 9 indicates that there are going to be 9 protons that are present in that fluorine atom. Remember that the number of protons is equal to the number of electrons at this point in time because for now, atoms are going to be neutral, so we also have 9 electrons associated with that atom. Remember that the top left number is the mass number, which refers to the number of protons plus neutrons. Since we already have 9 protons, 10 neutrons are necessary to be added to 9 in order to equal 19. So that's how we go through and figure these out. We do it exactly the same for the other ones as well. When we look at the sodium atom, It has an atomic number of 11, so that tells me that there are 11 protons, which also means that there are 11 electrons. In order to have 23 as our mass number, we have to have the number of protons plus neutrons equal 23. Since protons is 11, neutrons has to be 12. And again, we follow the same concept here for this gold atom. We have 79 protons and 79 electrons based off of its atomic number in the bottom left corner. Its mass number is 197, so we need to add 118 neutrons in order to get that to be 197. So again, make sure that you understand how to read these symbols. In addition to that, be sure you also know how to make the symbols. These are going to read up and down, so make sure you take time to go through. I want you to write the symbol this time from this information. Just the reverse of what we just did. Take a few moments and we'll be with you in just a moment. All right, so if we take a look at these individually, the very first one has 13 protons. If I go and take a look at my periodic table and find the element with 13 protons, I'm going to find that it is aluminum. In order to figure out the mass number, which is in the top left corner, I need to take protons plus neutrons. So 13 plus 14 is 27, so that goes in the top left-hand corner of the symbol. 13 goes in the bottom left, indicating the number of protons, the atomic number. We have 17 protons, 20 neutrons, and 17 electrons. Again, I look at my periodic table. I find that 17 protons is chlorine. When I add 20 to that, I get 37, so that means that the mass number is 37 and is placed in the top left-hand corner. And then lastly, we have 82 protons, that is going to be lead, and 82 plus 118 is going to give us 200. So again, making sure that you can work back and forth from this information. There may be times where I give you little bits and pieces of all of this information. It's very important that you can fluidly work back and forth between determining protons, neutrons, electrons, and its symbol, and vice versa. So make sure you're very fluid in going through and determining that information. So one thing to take into account is that chemical properties of atoms are determined by the number of protons and the arrangement of electrons around the nucleus. Remember that the number of protons is determinant of the type of atom that we have. So for example, all neon atoms are going to have 10 protons. And electron interaction is something that we're going to discuss a little bit later on, because the electron interaction will indicate to us how different atoms bond with each other, how they share electrons, how they might donate electrons. It's basically how chemical bonds are formed between different atoms. We define element as a pure substance in which all atoms have the same atomic number. However, that does not necessarily mean that they contain the same number of neutrons. Remember that the number of protons is based off of the atomic number. So if an element has the same atomic number, it means it's going to have the same number of protons throughout. Again, neon is going to have 10 protons. It may or may not necessarily have 10 neutrons. That is going to be because we have these things that are called isotopes. And isotopes of the same element have the same number of protons, but a different number of neutrons. So isotopes will be of the same element. Remember that isotopes contain the same number of protons, so you may have, in this instance, multiple isotopes of silicon. In this case, we have 3 different isotopes. We would use silicon 28 to describe the first isotope. Remember, the 28 is the mass number, that's protons plus neutrons. Silicon 29 to describe the second number, and silicon 30 to describe the third number. All 3 of these have 14 protons, but because the mass numbers are different and the atomic numbers are the same, that is indicative of them all having different number of neutrons. Most elements have a variety of different isotopes. Not all of them will have 3. Some will have 2, some will have 1, some will have 7 or 8, depending upon the element that we're looking at. There really isn't necessarily a way we can go through and predict that. There are 286 isotopes that occur naturally, and if you think about it, there's roughly 92 elements on the periodic table that occur naturally. So, roughly 3-ish isotopes per element on the periodic table. Again, that's not evenly distributed. That is just a number that's distributed throughout. I also want you to take a look at the percentages in the top right-hand corner there. Not all isotopes appear in the same percentage. That is, because silicon has 3 isotopes, it doesn't mean that each isotope occurs 33.3% of the time. In this example, silicon 28 appears 92.2% of the time, significantly more than that of silicon 29 and that of silicon 30. So the distribution of isotopes is different, and that distribution of isotopes leads us to what is called the average atomic mass or molecular weight or atomic weight. There's a variety of ways to describe it, and that is the decimalized number that you see on the periodic table. So go ahead and take a look at the periodic table and look at silicon. Silicon's average atomic mass is 28.09. All right, that is what is known as a weighted average of all 3 of those individual isotopes. I know I'm getting a little bit ahead of myself, but I want you to keep in mind that that number is something that's going to be very important to us as chemists as we continue to move forward in this course. So take a look at all of the different isotopes and the different atomic masses that are listed here. Hydrogen has 3 isotopes, but the most abundant one is that very first one. 99.985% of all hydrogen is that first isotope where we just have 1 proton and no neutrons. And then you have a second and third isotope below. Most of helium is helium-4. That is that there are 2 protons and 2 neutrons. I'm moving forward to lithium. Most of lithium is lithium-7 with 3 protons and 4 neutrons. There's a little bit of lithium-6 with 3 protons and 3 neutrons. And you can see as you go through, there's a variety of different isotopes that apply to each individual element that is on the periodic table. Some have 1, some have 2, some have 3. As you would continue further up the periodic table, you tend to find that there are more relative isotopes. I also want you to notice that the abundances are different for each individual isotope within each element as well. They're not all 33% or 50% or 100%. Many of them have a variety of different weights that are associated with them. Again, different isotopes mean that different atoms of the same element can have different masses, right? If we add in more neutrons, we end up finding that those specific isotopes have a greater mass, right? Hydrogen's mass number for its most abundant isotope is 1, but for its second most abundant isotope, it's 2. Again, the mass number of that being 2. And then hydrogen also has an isotope with a mass number of 3. So how do we get the mass of a sample of an element? If I were to take a chunk of an element, it's very unlikely that I get just one individual isotope of that element. So how do I take the mass of that particular element? And what we do is we take what is called a weighted average. So I want to take a step back from chemistry for just a moment and want you to think about the term weighted average. Many classes that you've taken either in college or in high school had a weighted average associated with them. And I'll give you an example from my classes that I teach at a local high school. In one of my classes at a local high school, tests are worth 65% of their grade, while labs are worth 20% and homework is worth 15%. So it would stand to say that tests and exams are worth significantly more of their average, because it's worth 65% of their grade, than that of labs and homeworks. So that means that their grade is going to be more weighted towards that 65% than it would be the 20 and the 15. And it's very similar to these isotopes and these weighted averages that you're going to find on the periodic table, is that you're going to find that the average atomic mass, that is that decimalized number that's on the periodic table, you're going to find that that's much closer to one of these isotopes that has a higher abundance associated with it. So the atomic mass that I've been referring to is the calculated average for the mass of isotopes of an element that's on the periodic table. Again, it's that decimalized number. So if I look at hydrogen, it's 1.008. If I look at lithium, it's 6.94. Beryllium, 9.012. All of those are weighted averages that you're going to find present on the periodic table. Now, how do I calculate that? Is based off of this information here. You simply take the mass of each isotope and multiply it by the decimalized form of the percentage and then take the sum of those values. So for example, I'm looking at lithium here. Lithium has 2 isotopes, one with a mass of 6.015 AMU, and we'll talk about what that means in a moment, and then one that is 7.016 AMU. So there's 2 isotopes that are here. I take each individual weight and I multiply it by the percentage. Now remember that percentages in decimalized form have been divided by 100. So notice I'm not taking 6.015 AMU and multiplying it by 7.42, but rather I'm multiplying it by 0.0742. You divide that percentage by 100 to get the decimalized form of the percentage. I do the same thing for the second isotope. I take 7.016 AMU and multiply that by 0.9258, and what I get is 6.50 AMU and 0.446 AMU respectively for each multiplication I did. I add those two together and I get 6.94, which is exactly what I find on the periodic table. So given any set of isotopes and their weights, you can very easily determine what the average atomic mass is going to be on the periodic table, or the atomic mass as it's listed here. Now again, take a look at the decimalized number that's on the periodic table for lithium. This is the atomic mass and molar mass. It should be the exact same value as you go through and calculate. And we're going to use this number quite extensively as we work through some materials a little bit later on. So it's very important that you know how to calculate this, but even more importantly, know how to utilize it a little bit later on. A couple things to think about before we go through and do more calculations with this. Remember that this is an average. It's a little bit different than taking a normal average where we just take 2 numbers, add them together, and divide by 2. A weighted average is a little bit more different than that. and it's still an average just the same. So what that means is that if I take the average of two values, regardless of whether it is a normal average or a weighted average, the numerical value should be in between the highest and lowest values. So if I take a look at that 6.94, I find that it is between 6.015 and 7.016. In addition to that, I can take a look at the percentage and get a better idea of what isotope's mass it should be closer to. Most of the isotopes in a sample of lithium are lithium-7. So what that means is that my numerical value for the average atomic mass should be closer to 7 than it should be to 6, because the percentage of isotopes that are 7 are greater than that of 6 significantly, right? 92.58% of a sample of lithium is lithium-7. So that tells me that the average should be much closer to 7 than it should be to that of 6, all right? So I have a sample problem for you here. It's exactly the same as what we just did. You just simply need to take the mass and the abundance and multiply them together for each of these, and then add them together when you're done. So before we even start this problem, I want us to get a good idea of what we're looking at here, because if we have a rough idea of what number we're looking at, it's going to make it so much easier for us to go through and calculate it a little bit later on. We have a relative mass of chlorine 35, and it gives us the AMU of 34.97. If you want to know why it's not 35 exactly, you can ask me later. And its abundance is 75.53%. And the relative mass of chlorine 37 is 36.97 AMU, and its abundance is 24.47. What is the atomic mass of chlorine? First off, I know it has to be somewhere roughly between 35 and 37, because those are the highest and lowest values that are given. In addition to that, I'm venturing that it's going to be closer to 35 than 37, because 75% of the mass of chlorine is going to be that isotope with the mass of 35, as opposed to the one with the mass of 37, which is only 25%. So I'd like you to take a moment, pause the video, go through, calculate that average atomic mass, and see if we get what we've predicted. I'll be back in just a moment. So here's the math done for you. Atomic mass here, 34.97 AMU. We're multiplying it by the decimalized form of that percentage, 0.7553. And then I'm going to add to that 36.97 times 0.2447. Sometimes it's best to do this separate from one another rather than doing them combined into one type of problem, but you can do it however you feel the most comfortable. Regardless of what happens, when I add them together, I end up with 35.46 AMU. And if I look at the periodic table, that's roughly I usually use 35.45 personally, but it's roughly the same as what I would have on my periodic table. And first off, I need to check and see, is it between 35 and 37? Yes, tick 1, done. Is it closer to 35 than 37? Yes, tick 2, done. So, that being said, you should be able to very easily go through and solve these problems. Just make sure that you take the percentage and put it in the decimalized form. That is the number one area where I see the most mistakes from my students. So again, some tips and tricks. If you have more than 2 isotopes, you'll need to repeat this procedure with 3 or 4 calculations rather than 2. So don't just go through and do 2 calculations. If you see 3 isotopes, you need to do 3 calculations and then add them together. Watch your significant figures, and then remember, it has to be an average. It has to be in between the highest and lowest values, just like we discussed, and we can make a prediction as to which isotope it's going to be closest to based on the percentages that are given. You also need to include your units, and for right now, you can include AMU or grams per mole. We'll talk about the latter in the future, but either of those are perfectly acceptable units for this particular calculation. All right, so I've got one more practice problem here associated with calculating average atomic mass. So let's take a look and read through this quickly. It says a sample of a chemical element has 3 isotopes, one with a mass of 23.985 AMU and an abundance of 78.70%, another with a mass of 24.986 AMU and an abundance of 10.13, and one more with a mass of 25.983 AMU, and with an abundance of 11.17, and what is the average atomic mass of the sample? So in this instance, we have 3 individual isotopes that we need to take the average atomic mass of, but we follow the exact same rules that we did before. We have use the pen, Jude. That's one of our isotopes, another one of our isotopes, and a third of our isotopes. So all we need to do is take the individual mass of the isotope and multiply it by the abundance. So 23.985 times, and again, that needs to be in decimal form, so 0.7870 plus 24.986 times 0.1013 plus, I'm going to write this down here at the bottom, 25.983 times 0.1171. Now, when I add all of those together, it should be somewhere between roughly 24 and 26. And what I notice here is that the highest abundance isotope is that's closest to 24. So when I go through and calculate, it should be closer to 24. So let's go through, do some math, and see what we come up with. My mistake, I did realize that this should be 0.1117, but what I end up with is an average atomic mass of 24.31 AMU. And it asks us to identify the element from the sample based off of the periodic table. So go and take a look at the average atomic mass. You're going to find that that is closest to that of magnesium, all right? So again, take your time. It's not that difficult to do. Just again, make sure that you read the question very carefully, identify the information, the problem that you have, and take some time and go through and solve for it. So what we're going to do now is we're going to take a little bit of a step back into the mid-19th century, where we've gone through and discovered many different elements, but rather than just kind of organizing them alphabetically or organizing them based on their relative mass, we want to try to organize them in a way that represents their reactivity with other materials. And in 1869, Dmitry Mendeleev designed the periodic table, the basis of the current day periodic table we use today, by arranging elements in increasing atomic mass with elements with similar properties repeating in columns. So if we take a look at the periodic table on the right-hand side here, you'll notice that if you go left to right, the elements increase in mass, very similar to how elements increase in mass on our current day periodic table. So you look at lithium, which has a mass number of 7, beryllium 9.4, boron 11, carbon 12, nitrogen 14, etc. And if you look at the second row on the periodic table, you see something very similar, where it goes lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, etc. Notice he didn't just continue moving forward and just continue them in a line here. He stopped and then restarted with a new line, a new row, if you will, and then repeated this process over and over again. Well, how did Mendeleev know to go through and do that? Well, it all depends on the reactivity with oxygen. So for example, if we look at the top part where it says group 1, and underneath that it says R2O, what that means is that everything in that column reacts with oxygen in a 2-to-1 ratio. So for example, hydrogen reacts with oxygen to form H2O. Lithium reacts with oxygen to form Li2O. Sodium reacts with oxygen to form Na2O, and so on as you go down the group. And what you notice is if you look at the current day periodic table, the group is relatively unchanged. There are a few elements that are in there that do not belong for a variety of different reasons, but they also reacted with oxygen in the same way. In the second group, very similar, you see RO, meaning that that particular element or the elements in that group react in a 1-to-1 ratio. So beryllium and oxygen would be BeO, magnesium and oxygen, MgO, calcium and oxygen, CaO, etc. And if you look at the second group on the periodic table, you see something, again, very similar. Now, again, there are some elements there that don't belong for a variety of reasons. One thing I want you to notice is if you go down the group that starts with silicon, and you see silicon, and then you see a blank, and then you see SN, and then you see PB. So I'm in group number 4, and on the right-hand side of group number 4, you see SI, which is 28, and then you see a blank space where there's 72, and then down below it you see SN at 118, which is 10, and below that PB, which is 207. So Mendeleev not only mapped the periodic table, but this is what's really amazing about his work, is that he left a spot on the periodic table that there wasn't quite an element that fit that particular pattern. And what he did is he left a spot blank, stating that there is an element there that has yet to be discovered, and that is actually the case. Germanium now fits there, which had not been discovered during the time in which Dmitry Mendeleev built the periodic table. So not only is it organized in a very similar way that our current periodic table is organized, but he was also smart enough to know where to leave spots and blanks for elements that had not yet been discovered. How cool is that? Pretty neat. But this is the basis of the modern day periodic table. The first thing we're going to define are periods, which are the horizontal rows of elements that are on the periodic table, and these are represented by standard numerals. So if we look on the left-hand side of the periodic table, you see period, and then you see 1, 2, 3, 4, 5, 6, and 7. They go across the periodic table. Please make note that there are purple elements down at the very bottom. So notice in period number 6, you have 55, 56, 57. It jumps down to 58 through 71. Those first group of purple elements, the top row rather, is in the 6th period on the periodic table. And then the one underneath it is in the 7th period on the periodic table. Big reason why we do that is so that way all of the elements actually fit on a standard 8.5 by 11 sheet of paper. And then our groups, which are inherently more important than knowing the period number, our groups are vertical columns that are on the periodic table. Sometimes they're referred to as families as well. And these are Arabic numbers and Roman numerals. So you see group 1A, group 2A, you see a bunch of group Bs, and then it's 3A, 4A, 5A, 6A, 7A, and 8A, or group 1 through 18. Either way is perfectly fine. But there are 4 common groups of element names or names of groups that you're going to need to know for this particular course. The first group I'm going to want you to know are the alkali metals, and this is the group that is on the far left-hand side of the periodic table. The alkali metals are the general name for the first group, group 1A on the periodic table, and they're named so because when they react with water, they typically form substances that are basic in nature. These are soft, shiny, readily react with water. The lithium is something that you can actually literally take and cut with a plastic fork. It's very, very soft and easily break apart, but it readily reacts with water. You've probably seen videos on YouTube of people taking lithium, sodium, potassium, things like that, dipping it in water and watching the reaction take place. It's quite violent. The next group over is the alkali earth metals, and this is the general name for the second group on the periodic table. We'll refer to that as 2A. And they're similar to alkali metals, but they're less reactive with water. You do find these often in the earth, hence the name alkali earth metal. So first 2 groups on the periodic table you are going to need to know the name for. Our last 2 groups on the periodic table also have very important names. The first one is group 17. That is the second to last group on the periodic table, and those are known as halogens. The term halogen literally comes from the term meaning salt forming. And these are typically room temperature gases that are quite reactive, things like fluorine, chlorine. Bromine's actually a liquid, iodine's a solid, but they tend to be quite reactive as well. And then on the far right-hand side, you have what are called noble gases, and that's the general name for group 18. These are very unreactive. And so what we can do is we can play basically a game of Battleship. If I give you a period number and a group number, you should be able to tell me the element that I am discussing based off of that location on the periodic table, again, like a Battleship grid. So that being said, what I'd like you to do is to pause the video and take a few moments and go through and determine which element we are discussing based off of this descriptive information of its location on the periodic table. Take a few moments, work through that, and we will be back here in just a moment. So again, we're going to just utilize these like a battleship map, find period 3, go across until you find group 4A. You are going to be looking at silicon. The period 4 noble gas, all the way down to period number 4, your noble gases are group 18 on the far right-hand side of the periodic table. That's going to be krypton. Period 2, alkaline earth metal, we go to period number 2 and go across, we find that it is beryllium. And the period 3 halogen, again period 3 all the way across chlorine is going to be the period 3 halogen we're looking at. So again, just utilize this like a battleship map and it should be fairly easy to go through and tackle. So again, when we look at the spacing of the elements that are on the periodic table, you may find that the periodic table kind of jumps around a little bit, particularly if you're looking at elements 58 through 71 and 90 through 103. And we've just kind of snipped these out of the location where they would normally find on the periodic table and kind of dip it down to the bottom. Now you may notice that there are some places where elements jump here and there on the periodic table. That has to do more with the number of electrons that are in its outermost shell and the levels and sublevels and orbitals that those electrons exist in. Again, beyond the scope and sequence of this course, don't worry about it too much. If you are concerned about it, I have an electron configuration video that you are more than welcome to take a look at a little bit later on. So let's talk a little bit about some of the differences of the elements that are on the periodic table. And again, Mendeleev did this based off of how they reacted, but there are also multiple trends that are present on the periodic table that were kind of a happy accident in regards to how they were formed just based off of their reactivity. The first one we're going to look at is the difference between metals and nonmetals and their locations on the periodic table. Metals are elements that have luster, meaning that they are very shiny when you look at them. They're very good at thermal conductivity, meaning that they retain and conduct heat very, very well, as well as electrical conductivity. There's a reason that wires are made out of metal. In addition to that, metals are also very malleable, meaning that they have the ability to bend, flex, and you can mold them into certain shapes. And things like copper, zinc, lithium, silver, they're all considered metals. Nonmetals are elements that have no luster, meaning that they're very dull. They have no thermal or electrical conductivity, meaning that they don't retain heat or electricity very well, and are not malleable. They tend to be very brittle. These are things like sulfur, oxygen, fluorine, iodine. You can see on the right-hand side there, they're very much in their powdered form. They're not going to be able to retain electricity or heat. They don't have much luster. They're not flexible when you try to manipulate them. They just kind of break apart into much, much smaller pieces. Now, most elements on the periodic table are metals, and what I'd like you to do is notice the stair step that's on the periodic table. If you've not done so, go ahead and draw the stair step on your periodic table, starting at just to the left of boron, and just work a stair step down the periodic table until you get to the very end. Everything to the left of that stair step is considered a metal by definition, and everything to the right of the stair step is considered a non-metal. Now, there are some elements that are touching that stair step that are kind of exist properties that are metal and non-metal. Those are called metalloids. I wouldn't stress on that for this particular course. Just know that everything to the left of the stair step is a metal, and then everything to the right is a non-metal. So again, take a moment, pause the video. Based off of the information we just discussed, go through and evaluate your knowledge of the information we just took a look at. Take a few moments, thank you. So which of the following is a property of most metals? Most metals are going to be malleable. That means that they have the ability to bend and mold, and you can take them and put them into a variety of different shapes. Which of the following is a metal? We're looking for something to the left-hand side of the stair step on the periodic table. Again, that is going to be C. Now, the explanation for periodic law, the reason why that those particular elements bond in a certain way, has to do with the arrangement of the electrons that are found within an atom. Mostly the outermost electrons. These are the ones that are of most interest because these are the ones that are involved in chemical bonding. There are also electrons that are called core electrons that are not the outermost. These are the ones that are further inwards, closer to the nucleus. So while electrons are free-flowing and moving around the nucleus, some electrons are just naturally further away from the nucleus than the others. These are the ones that are going to come in contact with other elements that the chemical's trying to bond with, and those are the ones that are going to interact to create chemical bonds. Core electrons are the ones closer on the inside. You can see that we're utilizing the Bohr model here with the rings. We know that that's not fully an accurate representation of the model of an atom, but the ones that are on the outside are the ones that are most likely to interact with other elements, while the ones that are on the inside aren't going to interact with other elements. So being able to determine the number of core electrons and the number of outermost electrons actually becomes quite important, because that gives us an indication of what types of bonds can be formed based on the number of outermost electrons that different elements have on the periodic table. So valence electrons is another term for the outermost electrons of an atom, and the number of valence electrons in an atom is solely dependent upon its location on the periodic table. It's a periodic property that really helps explain the reactivity that Mendeleev was seeing when he went through and designed the periodic table. And as you see here, it's very, very simple to determine the number of valence electrons that are present in a given atom. In the very first group on the periodic table, each of those elements has one valence electron. In the second group, 2 valence electrons. We skip all of those ones that are in the middle there, and we go to group 13, which has 3 valence electrons. 14 has 4 valence electrons. 15, 5, 16, 6. Our halogens have 7, and our noble gases have 8. So if we know the element in question and we know the number of valence electrons, we can figure out the number of core electrons, because the total electrons is going to be the core electrons plus the number of valence electrons. We can do a little bit of math and figure out how many core electrons an element is going to have based off of its valence electrons and the total number of electrons it has. So, as I mentioned before, the first column has 1 valence electron. All other electrons are considered core. The second column has 2 valence electrons. All other electrons are considered core electrons. And the trend continues through your main group elements. That is, the ones that are not the shorter groups that are found in the middle of the periodic table. So let's run through an example. Calcium has 20 total electrons. We know that based off of its periodic table location. We know that calcium has an atomic number of 20. Remember that the atomic number is equal to the number of protons, which for now is also equal to the total number of electrons it has. There are 2 valence electrons, so the remaining have to be core electrons. Well, if there's 20 total electrons and 2 are valence, that means that 18 have to be core electrons. So based off of the information of the location of the element on the periodic table and the relative number of valence electrons, you should be able to determine the number of core electrons that are present. So the next thing I want you to do here is to determine the number of core electrons and valence electrons that are in the following elements. Take a few moments and we'll come back and finish up our discussion for this evening. So starting off with bromine, if you look at bromine's location on the periodic table, we find that it has 35 total electrons, and based off of its periodic table location, it also has 7 valence electrons. So the number of valence electrons plus core electrons will equal the total number of electrons, so therefore there has to be 28 core electrons. Boron has a total of 5 electrons. It has 3 valence electrons based on its periodic table location, so it has to have 2 core electrons. And then lastly, neon has 10 total electrons. It's in the noble gas column with 8 valence electrons, so therefore also has 2 core electrons. So again, pretty easy to figure out based off of its periodic table location, its atomic number, and then you can very easily determine the number of core and valence electrons based off of that information. So the last couple things I want to go through and discuss for this evening is that elements can be classified based on their electron configurations. That is, the information that we get from how many outermost electrons they have tells us what type of element it is. And I go back and talk about the noble gas elements that are on the far right-hand side of the periodic table. They're unreactive because they have a full outer shell of electrons. You may be familiar with something that's called the octet rule. Now, that's not familiar with it. We'll talk more about it when we get to bonding, but most elements are most stable when they have 8 electrons in their outermost shell. And all the noble gas elements that are on the right-hand side of the periodic table have 8 electrons in their outermost shell. The only exception to that is helium, and helium only wants to have 2, and therefore, because it's the second element on the periodic table, has 2 electrons in its outermost shell. That provides us with an explanation as to why they are so unreactive, is because they have no desire to either take in or give up electrons in order to bond with other elements on the periodic table. A couple of other terms I want to make sure that you know. Representative elements, sometimes these are referred to as main group elements as well, are located in the first 2 columns, and then the other 6 columns for the representative elements are on the right-hand side of the periodic table. Transition elements are the ones that are in between the 2 groups of representative elements. These are things like scandium all the way to zinc. You have 10 groups that are there that are transition elements. Intertransition elements are the ones that are located on the very bottom part of the periodic table. They're the ones that we kind of snipped and took out and replaced down at the bottom. You may see like the continuity error going from 57 to 58. 58 through 71 is represented on the bottom of the periodic table, along with 90 through 103. So again, based off of this information, we should be able to very easily tell locations of elements, playing sort of a battleship style game. What is the noble gas found on the 3rd period of the periodic table? The 3rd period is that sodium period going across, and then the noble gas that's going to be found there is going to be argon. The alkali metal in the 4th period, again, alkali metal is that first group on the periodic table. 4 periods down, you're looking at potassium. So that pretty much rounds up everything we're going to be taking a look at for tonight. I really hope you enjoyed the video. I hope this helped explain a variety of different things, including how we determine the number of protons, neutrons, electrons in an element. Also hopefully helped you determine the average atomic mass, the design of the periodic table, and how we go through and identify elements based off of their location, as well as some of their properties. So hopefully you liked the video. If you did, make sure you give it a like, subscribe if you're interested for learning more, and thank you so much for watching for today. We'll see you very soon. Bye.